Hello everyone. So for today, we're going to answer 3 physics problems that we got in the university physics book. So let's get started. For our first problem, which is problem number 1, it is related to angular velocity and acceleration. So an airplane propeller is rotating at 1860 rev per minute. Compute for the propeller's angular velocity in rad per second and the time it takes for the propeller to turn to 40 degrees. So we need to compute for the angular velocity in rad per second, and we also need to solve for the time it takes for it to turn through 40 degrees. So for the solution, 1 RPM. So for the first one, 1 RPM is equal to 2 pi over 60. So which is simplify pi over 30 rad per second. So we're going to multiply 1860 rev per minute to pi over 30 rad per second. So we got 62 pi rad per second, or 194.78 rad per second. So we got the angular velocity of the propeller. So next, for letter B, we need to compute for the time it takes for it to turn to 40 degrees. So the first thing we need to do is to convert degrees to rad. So the formula in converting degrees to rad is theta degrees times pi over 180 degrees, which is equal to rad. So 40 times pi over 180 degrees, which is equal to 0.698 rad. So for us to solve for time, remember the formula: rate times time is equal to distance, or velocity times time is equal to displacement. So we're going to use omega times time, which is equal to change in theta. So the formula in computing time is equal to change in theta over omega. So here in our problem, the initial omega is 0, and the theta is 0.698 rad. So 0.698 rad minus 0 over our omega, which is 194.78 rad per second. So we got 3.58 times 10 raised to negative 3 seconds. So that's the time it takes to turn to 40 degrees, which is it is a little amount of time. So there you have it. We answered the needed answers in problem number 1. So for problem number 2, it is connected to rotation with constant angular acceleration. So the problem is a circular blade 0.180 meters in diameter starts from rest. In 6.35 seconds, it accelerates with constant angular acceleration to an angular velocity of 148 rad per second. Find the angular acceleration and the angle through which the blade has turned. So for this problem, we need to find the angular acceleration and the angle through which it has turned. So for us to find the angular acceleration, we need to use the constant angular acceleration formula, which is this one. So we got an answer of 23.31 rad per second squared. So we found the angular acceleration, which is 23.31 rad per second squared. So we need to find the angle through which it has turned. So the formula that we need is this one: theta minus theta initial, which is equal to omega final plus omega initial divided by 2 multiplied to the time. So 148 rad per second minus 0, because I think it starts from rest, so it's 0, and then divided by 2 times time, which is 6.35 seconds. So we got an answer of 469.9 rad. So we need to convert rad to degree. So the formula is 1 rad times 180 over pi. So we're going to convert 469.9 rad to degrees, and we got a very high value of degree, which is 26,923.29. So that's it. So for problem number 3, which involves energy in rotational motion, here is the problem that we need to solve. So a hollow spherical shell has mass 8.05 kg and radius 0.220 meters. It is initially at rest and it rotates about a stationary axis that lies along a diameter with a constant acceleration of 0.870 rad per second squared. What is the kinetic energy of the shell after it has turned through 5.0 rev? So here, these are the formulas that we need in order to solve this problem. So we need the formula in getting the kinetic energy, which is K is equal to 1/2 times I omega squared, wherein omega is rad per second. Constant angular acceleration, which is this one. And the formula of hollow spherical shell is 2/3 mass times radius squared. So the solution is here. So first we need to convert 5 rev to rad. So 5 rev multiplied to 2 pi over 1 revolution, 1 rev is equal to 31.42 rad. So first is we are going to use the constant angular acceleration in order for us to find the angular acceleration needed in the problem. So it's there. This one's 0 because it initially starts at rest according to the problem. So 2 times 0.870 times 31.42 to the rad. We have a square root there because it is in squared. So squared on the other side. And then we got 7.39 rad per second. And then the next one, we need to compute for the value of the hollow spherical shell. So we have a value of the mass, which is 8.05 kg, and the radius, which is 0.220. So we got the value of I, which is 0.2597 kg per meter squared. And then we computed for the things that we need in order to get the kinetic energy. We computed for I and we computed for omega. So we can now use the formula in getting the kinetic energy, which is 1/2 I omega squared. So we plug in the values that we have computed, which is 0.2597 kg per meters squared, multiplied to the omega, which is 7.39 rad per second squared. And then we got the kinetic energy of 7.09 joules. That's it. Thank you.